In this video, we're going to take a look at the idea of electric potential. Electric potential is probably one of the more challenging concepts in electrostatics. But let's start with something that we're familiar with, which is potential energy. The potential energy due to electrical charges is very similar to the idea of potential energy due to gravity. So for instance, if I have a mass and another mass, let's say this mass is a little rock and this is the Earth, we learned before that as we raise that mass up, it gains potential energy. And the reason is we're doing work against the force of gravity, and that work that we do translates into a change in gravitational potential energy. In terms of charges, imagine I had a positive charge here and a little negative charge. It would be the same idea. They're attracted to each other. If I was to take the little negative charge and move it away from the positive charge, I'd have to do work in order to do that. I'd have to use a force, and I'm moving it over a distance. And that's the work I would do. If I'm in a uniform electric field, the work that I'm doing, that force is equal to the charge that I move, that would be in this case the negative charge, times the strength of the electric field, times the distance that we move it. So this QED, the charge times the electric field times the distance, is equal to the work I would have to do. 2-point charges are not going to make a uniform electric field. We'll get into that later. But for now, you can say that the work done equals QE times D. And that work that we do is equal to the change in potential energy. And now this is electrical potential energy. So all these guys are equal. Now, if I was to release this charge, just like if I was to release a mass that was held above the surface of the Earth, it would move back down in the other direction, and you could have that potential energy turn into kinetic energy. So the same ideas apply here as applied when we learned about gravitational potential energy. A concept that comes in here that we did not use when we were doing gravitational potential energy is something which is called electric potential. If you look at the word up here, electric potential, you notice it doesn't say electric potential energy, it just says electric potential. Now imagine I have an electric field in space. I'm going to draw some electric field lines, and I were to place a charge here. Compared to another place over here, I'm going to call this place up here B, and I'm going to call this place down here A. The amount of potential energy I have at B will be different than A because it will take some work to move it from B to A. That change in potential energy is going to depend on how much charge I move. So we have this concept called electric potential, where instead of talking about the total potential energy change, we talk about the potential energy per charge. This idea is known as electric potential, and we abbreviate it with a capital V because the units of electric potential are the volt. And often, instead of calling it electric potential, we call it voltage. So what voltage is the difference between 2 points in space in their potential energy per charge. And this makes sense in electricity because there's a lot of charges involved. When we were doing gravity, we were dealing with chunks of mass. Here, we can be dealing with many, many, many charges. So it makes more sense to pull the charge out of it and talk about it in terms of just this voltage idea. Often we'll take that and write it as the change in potential energy equals the charge times the change in electric potential or voltage. Let's do an example of this to help you understand what we're doing. Now, if you find this confusing, don't worry, because it took me a long time to truly understand this idea when I was a physics major in college. But I did learn how to do the math in the meantime, so you might have to just be content with knowing how to do the math for a while before the concept really seeps in. It's a little bit of a complicated and abstract concept. All right, let's do an example here. Suppose an electron in the picture tube of a television is accelerated from rest through a potential difference of plus 5,000 volts. What is the change in potential energy of the electron, and what is the final speed of the electron? Okay, so change in potential energy, that's delta U, equals the charge times the change in voltage. Got to put a little delta there. We're talking about an electron, so we'll put in negative 1.6 times 10 to the negative 19 coulombs. Now you notice this time I put the negative sign in there. That's because in this case it matters. Okay, before, when we were dealing with forces and electric fields, we threw out the negative sign because we were determining the direction of the vectors using our common sense and our understanding of repulsion and attraction. Now, energy is not a vector, so you can have negative changes in potential energy and positive changes. And so we kind of have to stick with the negatives now. And as far as my voltage is concerned, it's plus 5,000 volts. If I plug those in the calculator, I come up with negative 8.0 times 10 to the negative 16 joules. So that's part A. B is finding the speed. We're losing potential energy and we're going to gain kinetic energy. I hope that makes sense. If I let go of this electron in this field, it's going to accelerate and it's going to gain some speed. And we can do this almost as if we did those problems where if you dropped a rock and its potential energy turned into kinetic energy, well, we can do the same thing here. So we can say that change in potential is going to be equal to the gain in kinetic energy. And since I'm starting from rest, I can just write 1/2 mv final squared. And if I solve that for v final, I'm going to get the square root of 2 times the change in potential energy. Not very good at making those, am I? Let's try that again. There you go, just a little guy. Over the mass. And we can plug all those numbers in. Leave myself lots of room. 2 times negative 8.0 times 10 to the negative 16 joules over the mass of 9.11 times 10 to the negative 31 kilograms for an electron. Now I do have this negative sign in here. If you think about it, I'm going to lose potential but gain kinetic. Really, this negative doesn't apply here, so I really should have said that delta U equals minus the change in kinetic, but you get the idea. Or we're gaining kinetic energy, not losing. So I'm going to lose that minus sign and change it to a plus. And if I plug that in the calculator, I get 4.2 times 10 to the 7 meters per second. One last thing we need to talk about before we go on this video is the relationship that you get when you actually have a uniform electric field. Now, to make a uniform electric field, you're not going to make it with point charges, but if you have plates of charges, it's horrible looking straight lines, but you know, doing the best I can here. Imagine in your infinite imagination that those are actually parallel plates. Now, if you have one side charged positively and the other side charged negatively, electric field lines always go from positive to negative. So I would actually have lines that connect these plates of electric field. And I'm trying to draw them straight and evenly spaced because at least towards the middle of this plate, not so much at the edges, this really does produce a uniform electric field. And if you have a uniform electric field, then the force is Q times E. And we saw that the work done before is going to be Q times E, the force times the distance. Now that work done is the change in potential energy. So if I replace that here and one more, I'm going to divide both sides by Q. And I'm going to get that the energy potential energy per charge equals ED. Well, potential energy per charge is our potential difference, equals E times D. And that's the strength of the electric field times the distance. And quite often, this D is we're going to talk about the distance between the two plates. That's actually going to become handy for us in many, many problems. So let's just do a quick example problem so you can see what I'm talking about. So what we're going to assume is that these plates that we have are charged up to a potential difference of 50 volts. Maybe we connected a 50 volt power supply to it. And the separation between these plates is going to be 0.050 meters. Now what we need to do is figure out what is the size of the electric field between them. What's the magnitude of the electric field? So what we can do is take our relationship over here, delta V equals ED, and solve it for the electric field. And I get the electric field is the potential difference over that distance. So that's going to be 50 volts divided by 0.050 meters. And that's going to come out to 1,000 volts per meter. Before, when we did electric fields, we said electric fields were measured in newtons per coulomb. You can actually show that a volt per meter and a newton per coulomb are exactly the same thing. And sometimes it makes sense to talk about it in terms of newtons per coulomb, and sometimes it makes sense to talk about it in volts per meter. But they're the same thing. And this little simple relationship is actually going to come in handy for us in several situations. But remember, this only works if you have a uniform electric field, which generally we only get if we have parallel plates.